you some important points regarding we can see the crystal structures. These are some of the important points regarding the crystal structures of the electrical materials. So basically here we are going to have four types of the crystal structures. One is the simple cubic crystal. Second one is the body centered cubic crystal, and the third one is the face centered cubic crystal, and the last one is the diamond cubic structure. So these are the four types of crystals that are going to occur in the nature. And in all these things, we are going to consider the unit cell as the cubic in nature. So in all these things, we are going to consider the unit cell as the cubic in nature, means all the sides are equal. So SCC means simple cubic crystal, BCC means body centered cubic crystal, FCC means face centered cubic crystal, and DCS means diamond cubic structure. Okay. So we will discuss the different properties in all these things. We will try to discuss. The first property is basically here number of atoms. So if you see in the case of the SCC, we are going to have the 8 corner atoms, because unit cell is going to have the cube is going to have the 8 corners. So therefore it is going to have the 8 corner atoms. Okay. And I've already told you, which is see, 1 corner atom is going to contribute the 1/8 portion of the volume of the atom in one unit cell. So therefore, now tell me, because of 8 corner atoms, how much amount of volume or number of full atoms which are going to present in a unit cell, which is 8 into 1/8. So therefore, what you are going to get? The value is 1. And here, the coordination number means, what's the meaning of coordination number? The number of atoms which are going to touch a specific atom is called as the coordination number. In the case of SCC, the coordination number is 6. Here A is nothing but it is we can say it is the length of the cube. It is the length of the cube. The side length of the cube or the edge length of the unit cell. Okay. Here A is equal to 2R, where R is the radius of the atom. Similarly, what's the packing efficiency? Here the packing efficiency is 52%, means the volume of the atoms which are going to occupy in a unit cell by the total volume of the unit cell. What's the meaning of packing efficiency? It's the ratio of the volume of the atoms which are going to occupy in a unit cell by the total volume of the unit cell. So if you try to figure out, we are going to get its value is equal to 52%. Then what is the empty space, which is 100 minus 52 is equal to 48. If 52 is filling by atoms, then remaining 48 is filled by empty space. Okay. And also, this is a very important point that you have to remember regarding the SCC. Now let's go for the BCC, means body centered cubic crystal. In this, we are going to have 8 corner atoms. Here we are going to have the 8 corner atoms, as well as we are going to have 1 body centered atom. So here we are going to have the 8 corner atoms as well as 1 body centered atom. And also here I already told you, because of 1 corner atom, it is going to contribute the 1/8 portion of the volume of the atom is going to present in one unit cell. And similarly, 1 body center atom is, this body center atom is completely, it is present in the unit cell. So now tell me, how many number of full atoms are there, which is 8 into 1/8 plus 1, which is nothing but 1 plus 1, which is equal to 2. So 2 number of full atoms are going to present in the case of the BCC. And in the case of BCC, the Polish number is 8. 8 indicates that these number of atoms are going to touch the a single atom. So therefore we can say the coordination number is 8. Whereas A is equal to 4R by root 3 in the case of BCC. Here A is nothing but, we can say, the unit of the edge length of the unit cell or the side length of the unit cell, where R is the radius of the atom. And what's the packing efficiency? In the case of BCC, the packing efficiency is 68%. Okay, and the empty space is 100 minus 68 is 32. So these values you need to remember. Basically, in the examination, they can ask you regarding this concept. In the case of FCC, we are going to have the 8 corner atoms as well as 6 face center atoms. So we are going to have 8 corner atoms and also 6 face center atoms, because in the case of cube, we have 8 corners and also we have 6 faces. So therefore, we are going to keep 8 corner atoms as well as 6 face center atoms. Now, I will try to tell you the number of full atoms which are going to present in the unit cell, which are nothing but, so because of 1 corner atom, 1/8 portion of the volume of the atom is going to present in one unit cell, and because of 1 face center atom, half of the portion of the volume of the atom is going to present in a unit cell. So 8 into 1/8 plus 6 into 1/2, then what you are going to get? 1 plus 3, which is equal to 4. And its coordination number is 12. And SCC having a coordination number of 12 means full number of atoms are going to touch the one unit cell. Sorry, full number of atoms are going to touch one single atom. So we can say its coordination number is 12. And the value of A is equal to 4R by root 2. Where A is the edge length of the unit cell or the the side length of the unit cell, which is equal to 4r by root 2. That is the radius of the atom. And if the packing efficiency is 74%, and if the empty space is 26, because 100 minus 74 is 26. Now let's go to the last thing, which is that DCS, means diamond cubic crystal. In this, it's a combination of both the BCC as well as FCC. Means here we are going to have 8 corner atoms as well as 6 face center atoms, as well as we are going to have 4 body center atoms. So here we are going to have 8 corner atoms as well as 6 face center atoms, as well as 4 body center atoms. So because of one corner atom, 1/8 of the portion of the atom is going to present in one unit cell, and because of one face center atom, half of the portion of the volume of the atom is going to present in one unit cell, and these body center atoms are completely, they are going to present in the unit cell. So 4 means all the 4 are going to present in the unit cell completely. So now tell me, 8 into 1/8 plus 6 into 1/2 plus 4 into 1, which is nothing but we are going to get, which is 1 plus 3 plus 4, which is equal to 8. So totally 8 number of full atoms are going to present in the case of the diamond cubic structure, as well as its Cornish number is 4. Its Cornish number is 4 means 4 number of atoms are going to touch the one specific atom. So therefore we can say its Cornish number is 4. And the value of A is equal to 8r by root 3, where A is the edge length of the unit cell, or we can say that it is the side length of the unit cell, where R is the radius of the atom. So the packing efficiency is for the DCS, which is 34%, then empty space is 100 minus 34, which is 66%. So I request you to remember this table, so definitely you can get at least one question from this concept. Sometimes they can ask you the coordination number, sometimes they may ask you regarding the side length, and also they can ask for the packing efficiency. So if you try to compute the packing efficiency, out of this, it is having the maximum value FCC, then second maximum is BCC, then comes the SCC, and the last one is the DCS. So if you see clearly, the maximum packing efficiency is for the FCC, then comes the BCC, then comes the SCC, and finally it goes for the DCS. Okay, this is the very thing we have to remember. Sometimes they may ask you, which is having the least packing efficiency means DCS, diamond cubic structure, and which is having the maximum packing efficiency means FCC, as you can see clearly from this one. So I request you to remember this table also. And one more important concept is, I will try to tell you the types of unit cells which are going to present, the types of unit cells which are going to present in the crystals. So basically there are 7 types. There are 7 types. So basically I will tell you all these 7 types also one after the another. So they are going to depend upon the lengths as well as the angles. So they are going to depend upon the lengths as well as angles. The lengths are A, B and C, and the angles are alpha, beta, gamma. I have given the representation also, you can see clearly here. So based on the lengths as well as angles, so we are going to get different unit cells. So based on that we can get different crystals also. So 7 types are there. So we will discuss one after the another. The first one is the cubic. See, this type of cubic I have already told you. Cubic unit cell we are going to use in the case of FCC, SCC, FCC, BCC, as well as the diamond cubic crystal. And all these things we have learned about the cubic only. So in the cubic, all the sides are equal. All the sides are equal. A is equal to B is equal to C, and all the angles are equal, and they are equal to 90 degrees. So in the case of cubic, all the sides are equal, as well as all the angles are equal, and they are perpendicular to and they have an angle of 90 degrees. As you can see clearly from this picture also. So all the lengths are equal, and all the angles are also equal, and they are equal to 90 degrees. The next one is a tetragonal. Tetragonal means this A is equal to B. So only 2 sides are equal, but the third side is not equal. Means only these 2 sides are equal, but the third side is not equal. Means it may have some large value. Okay. So A is equal to B, but both are not equal to C. And the angles are equal, and they are equal to 90 degrees. So this is the shape of the tetragonal. Then comes the orthorhombic. Orthorhombic means all the lengths are different. A is not equal to B is not equal to C. So you can see they have different lengths, but the angles are equal, and they are equal to 90 degrees. Okay. Monoclinic. Monoclinic means, yes, in this case also all the lengths are different, but only 2 angles are equal to 90, and the third angle is not equal to 90. So here also you can see all the lengths are different, and only 2 angles are 90, which is alpha and gamma. So you can see here alpha and gamma, they are 90, and the third one is not equal to 90. Okay. Then comes the hexagonal. As you can see, this is a figure of the hexagonal. So here this is the length A and this is the length B. Both are equal. Okay. But the third one is different. Third one is different. As you can see clearly, third one is different. And the alpha and beta are the 90, but the gamma is 120 in this case, okay, in the case of hexagonal. But if you want the exact ratio, means C is equal to C by A. If you want the exact ratio, it is equal to 1.633. So this is the exact ratio, means C is somewhat higher than A, but not very large. C is somewhat higher than A, but not very large, as you can see clearly from this one. So I request you to remember this value also. It's a very important thing here. So let me go for the other sketch in order to make it very clear. Okay, I will go for the yellow color. So this is a very important thing that you always have to remember. So in the case of hexagonal, only two sides are equal and the third side is having a different value, and two angles which are equal to 90 degree and the third angle is equal to 120 degree. And if you want the ratio of C by A, the ratio of the two lengths which are having different values, it is nearly equal to 1.633, means C is somewhat higher when compared to A. And rhombohedral means like this graph we are going to get. Yes, here also all the lengths are equal. But all the angles are equal, but they are not equal to 90. Yes, they have different value. So in the case of rhombohedral also, all the lengths are equal. And all the angles are also equal. But the only thing is they are not equal to 90 degree. So this is the figure that we are going to get. And finally, triclinic. So this is a triclinic. This is the seventh one, I can say. So here all the lengths are different and all the angles are also not equal to 90 degree. So they are not equal to 90 degree, means they have different values. Okay. So therefore we can say in the case of triclinic, all the lengths are also not different and all the angles are also different. They are not equal to 90 degree, means they have a different value. So all the angles are not equal and also they are also not equal to 90 degree. Then it's a triclinic. So these are the different types of unit cells that you can get. Cubic, tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral, as well as triclinic. These are the 7 types of unit cells we can get in the case of crystal structures. This is a very important concept. The next thing is the types of bonds. Let me try to discuss. Okay, we have 2 types of bonds. One is the primary bond and the second one is the secondary bond. So basically we have 2 types of bonds. One is the primary bond and the other is the secondary bond. So let me try to discuss in detail. So in the case of primary bonds, we have 3 things. One is the ionic bonding, second one is the covalent bonding, the third one is the metallic bonding. So ionic bonding means one atom is going to lose the electron compared to the other atom. Then we can say the type of bonding is going to present as called as the ionic bonding. Because one atom is completely losing its electron to the other atom. So because of this, then we can say the type of bonding is called as the ionic bonding. Covalent bonding means both atoms are going to share the electrons in order to become stable. Okay, And metallic bonding means it is a group of electrons. They are going to bond the ions in such a manner. That is the type of bonding is called as a metallic bonding. So in this, with the group of electrons, they are going to bond the ions in such a manner to become stable. That is called as a metallic bonding. And if you try to compare, the primary bonds and secondary bonds, primary bond is always stronger when compared to secondary bonds. So primary bond is always stronger when compared to secondary bonds. And if you try to compare within the primary bonds, then I can say metallic bond is always stronger when compared to other primary bonds which are nothing but ionic and the covalent. So if you try to compare within the primary bonds, metallic bond is always very stronger when compared to other primary bonds which are ionic bonding and the covalent bonding. Means you require a lot of energy to break the bonds in the case of metallic bonding, whereas you require less amount of energy to break the bonds in the case of ionic as well as covalent. More energy means more melting point. That is the reason metallic bonds are going to have the high amount of melting point. Listen carefully. Primary bonds are very strong bonds when compared to secondary bonds. And if you try to compare between the primary bonds, metallic bond is very, very stronger than compared to ionic as well as the covalent bonds. Because here, as they have the very strong bonds, so they have the very high amount of energy required in order to break the bonds, so therefore they are going to have the huge amount of melting point. So that is the reason the metallic bonds are going to have the high melting point. Means they require huge amount of energy to break the bonds when compared to ionic as well as covalent. So metallic bonds are very stronger when compared to other primary bonds which are the ionic bonding as well as covalent bonding. So in the case of secondary bondings, we have 2 things. One is the hydrogen bonding as well as the second one is the van der Waals bonding. See, hydrogen bonding is between the 2 atoms, whereas van der Waals bonding is between the 2 molecules. See, the combination of atoms is called as the molecules. So hydrogen bond is between the 2 atoms, whereas the van der Waals bonding is between the molecules. See, hydrogen bonding is going to occur because of the different electronegativity of the atoms. If one atom is going to have high electronegativity means it is going to attract the electrons toward itself. So definitely that atom will become partially negative charge and the other atom will become partially positive charge. So because of this, it gets a force of attraction. So this is called the hydrogen bonding. And the van der Waals bonding means you take two molecules. Then these two molecules will have a small amount of positive charge and a negative charge. So because of this, there's a force of attraction. That type of bonding is called the van der Waals bonds. And these are very weaker bonds. These are the very weaker bonds. So you can easily break them. Okay. So that is the reason primary bonds are very stronger when compared to secondary bonds. And if you try to compare between the primary bonds, I can say metallic bond is very stronger when compared to other primary bonds which are the ionic as well as covalent. But that is a very important concept that you need to always remember. Then comes the Miller indices. See, Miller indices, with the help of Miller indices, we can try to figure out the orientation of the plane. So first try to figure out the intercept of the plane on the axis. Basically, we have three axes, right? X-axis, Y-axis, and the Z-axis. So first try to figure out the value of the intercepts which are made by the plane on the X-axis, Y-axis, and Z-axis. And try to do the reciprocal of that. Then we are going to get the Miller indices for a corresponding plane. So therefore, as you can see clearly, it is a reciprocal of the intercept on the x-axis, a reciprocal of the intercept on the y-axis, a reciprocal of the intercept on the z-axis. So this is a very important thing. Always you have to keep in your mind. So always try to, for a given plane, first try to figure out the intercepts which are going to be made by the plane on the axis and do the reciprocal in order to get the Miller indices for that corresponding plane. So with the help of Miller indices, we can try to figure out the orientation of the plane. And always try to write the Miller indices only in the terms of the 1 as well as 0. So always try to write the Miller indices only in the terms of the 1 and 0. Okay. So this is all about the Miller indices. So let me tell you some important units that I definitely ask in the examinations. So some important units I will try to explain. Here E is equal to K into T. Where E is called as the thermal energy, K is called as the Boltzmann constant, and T is called the temperature. Temperature is always a measure in terms of Kelvin, and energy, it can measure in either joule or either it can measure in electron volt. So now I will try to find the unit of the Boltzmann constant. It can be either joule per Kelvin or either it can be electron volt per Kelvin also you can get. Then inductance formula, L is equal to N square by R. R is equal to L by mu L. If you simplify, what we are going to get? Mu into N square A by L, where L is the we can say inductance, and mu is the permeability, N is the number of turns, A is the area, and L is the length. The unit of the inductance is Henry, and the unit of the area is meter square, and the unit of the length is meter, and the unit of N is the number of turns. It's a number, so it's a dimensionless. It's a number, means it's a dimensionless. So what I can say now, here meter square and here meter. So meter cancels. Wherever meter is there, here it is Henry is there. So Henry per meter is nothing but it's a unit of the permeability. So mu is nothing but permeability. The unit of the permeability is Henry per meter. Then comes the capacitor formula. C is equal to epsilon A by B. Where C is called the capacitance, epsilon is called as the permittivity, A is called as the area, and D is called as the distance. And the unit of the capacitance is farad, and the unit of the area is meter square, and the unit of the distance is meter. So if you simplify, what you are going to get, the unit of the permittivity, which is farad per meter. Here meter square by meter means meter cancels, and if it comes downward, then you are going to get the unit of the permittivity, which is farad per meter. Then the differential velocity is equal to mobility into electric field. So this formula I already told you in my annual electronics classes, which is Vd is equal to mu into E. And Vd is the drift velocity. Small correction here. Vd means drift velocity. So Vd is equal to mu into E. So Vd is equal to mu into E, where Vd is the drift velocity and mu is the mobility and E is the applied electric field. And E is electric field means it is the ratio of the voltage by. So let me just 10 seconds. So E is nothing but electric field is equal to volt per distance. You know this formula, right? E is equal to V by D. E means voltage and D means distance. And the unit of the voltage is volt and the unit of distance is meter. So now I will try to write in terms of Vd means drift velocity. What is the unit of meter velocity? Meter per second or centimeter per second? Here I will take in terms of centimeter per second. And mu is mobility. And electric field is volt per voltage by distance. So voltage unit is volt and distance unit is meter or centimeter. So I take it centimeter. So if it's MP, what you are going to get centimeter square by volt per second, because I have taken the drift velocity unit is meter per second, and I have taken the unit of the electric field is volt per centimeter. So if you simplify, what we are going to get centimeter square by volt second. So these are the different parameters, and the units also very much important. The examinations they may ask. The final concept that I wanted to tell you is a very important concept, and you always have to keep in your mind. Here, this is a very important thing. Suppose there is nothing but A is called as the lattice constant, or it is also called as the edge length of the cubic unit cell. Suppose if you take a unit cell of cubic nature, there is nothing but it is sometimes it is called as the lattice constant, or it is also called as the side length of the cubic unit cell or the edge length of the unit cell. And what is M? M is nothing but it is the atomic mass of the 1 mole of atoms. But what capital M is nothing but it is the atomic mass of the 1 mole of atoms. Now, in the case of 1 mole of atoms, how many atoms are there? That is called the Avogadro number, which is capital N. So capital N is called as the Avogadro number, or these number of atoms are going to present in 1 mole of atoms. Then what is rho? Rho is nothing but the density of the corresponding element. Rho is called density of the corresponding element. Then what is small n? Small n is nothing but these many number of lattice points are going to present in the 1 unit cell. So these many number of unit cells are going to present in 1 unit cell. So now I want to give you some relation between these values. I wanted to very important question. So I wanted to give you some important relation between these values. There is nothing but lattice constant, and this also called as the edge length or the side length of the cubic unit cell, where M is nothing but capital M is nothing but atomic mass of the 1 mole of atoms. Atomic mass of the 1 mole of atoms, where capital N is the Avogadro number of the these number of atoms which are going to present in the 1 mole of atoms, where rho is nothing but the density of the element, and the small n is nothing but these number of lattice points which are going to present in the 1 unit cell. So now here I already told you what is M. Capital M is atomic mass of 1 mole of atoms, where capital M is nothing but Avogadro number, or these number of atoms are going to present in 1 mole of atoms. Then what is the relation? M is equal to N into number of mass of one atom, mass of each atom, mass of each atom. Here I can write each atom, or one atom also you can write. Anything is correct. So here I will write mass of each atom I will write here. So mass of each atom is nothing but capital M by capital N. So mass of each atom is equal to capital M by capital N. Where capital M is nothing but atomic mass of 1 mole of atoms, where N is the Avogadro number of these number of atoms are going to present in 1 mole of atoms. So if you do the ratio, then what you are going to get? The mass of the each atom you are going to get. Then what is the mass of 1 unit cell? What is the mass of 1 unit cell? See, in the case of unit cell, we have n lattice points. Means in these lattice points we can give the atoms, right, in order to become in order to get the crystal, right? So then we have small n number of atoms are there, and each atom is having a mass of capital M by capital N. So if you do the product, then what you are going to get? It is the atomic mass of the 1 unit cell. So listen carefully. In 1 unit cell we have n lattice points. So n lattice points means here we can give this number of atoms to make a crystal. So n atoms are there. Into what's the weight of, what is the mass of each atom? It is capital M by capital M. So if you do the product, then what you are going to get? The mass of the 1 unit cell. And if you know the formula, what is density? Density is equal to mass by volume. So I want to apply this formula only for 1 unit cell. So I want to apply this formula for only for 1 unit cell. Then what is the mass of 1 unit cell? So what is the mass of 1 unit cell? Which is nothing but this value, right? So small n into capital M by N. And density is nothing but rho. Then what is the volume of 1 unit cell? See, 1 unit cell and side length of the as is a cubic, then all the lengths are equal. So what's the volume? A cube. That's it. So if you simplify, you are going to get finally A is equal to small n into capital M by capital M into rho all the power of 1 by 3. So it's a very important relation. Definitely these type of questions will be asked in the examinations. So I explained everything. So always remember, what is the capital M? Capital M is nothing but it is the atomic mass of the 1 mole of atoms. In that 1 mole of atoms, how many atoms are there? Means N. This is the Avogadro number of atoms. This one number of atoms are going to be present. So M is equal to N into atomic mass of each atom. M is equal to N into atomic mass of each atom. So if I give you a small example, how can I give you? It's very simple. Suppose you take some box. Suppose if I have 3 balls, and each ball is of 1 kg, then what is the total mass? 3 kg. So 3 kg is equal to number of atoms are, number of balls are 3. So 3 into 1 kg, right? Here, this 3 kg is nothing but total mass. of the 3 balls. But 3 is the number of balls into mass of each ball. Mass of each ball. Same thing. So 3 is nothing but this one is called as the capital M, and this is called as the capital N, and is the mass of each atom. So it's the same thing. So capital M is equal to capital N into mass of each atom. So where M is nothing but the atomic mass of 1 mole of atoms. In that, how many atoms are there? Avogadro number of atoms is N. Into this is nothing but the mass of 1 atom. Okay. So this is a very important thing. Always you have to remember. So I have given the small this one in order to understand this concept also. So these are some of the important points regarding the crystal structures of the electrical materials. Definitely you can get at least one question from these concepts.